probably get another little burst just around about now. So every time I start at 5 past, about 8 past, another batch of people arrive. I might as well start now. Okay, so hello again. So last week I was talking more about transactions, and we almost finished those slides. So I'll finish them off first up, and then we're going to talk about performance. This is one of 2 lectures on performance. Alan's giving the second one while I'm wandering around Central Australia after Easter. So this one is talking about performance in a general sense, and Alan's one is going to be specifically about performance modelling and queuing theory. So we talked about good old ACID transactions and wonderful things. They have some issues, and based on the assumptions of trustworthiness and timeliness. If you can't meet those, then they're not usable. So there are a large number of other transactional models. You obviously need support for writing these types of correct systems, so there are other models around. Even check-in, check-out type systems are effectively transactional. So computer-aided design, source code, where you've got a unit of work, a whole batch of changes, and you put them into the system as an atomic unit, and you want to be able to compare it as an atomic unit and move from one version of the source code or the document to another. So although you may not think that being transactional in the sense of moving from one state to another in a set of consistent changes, it's exactly that. So there are models around based on this idea of here's the system, we move to another one, so checking in and checking out. There are any number of business integration tools around there. Some of the web services standards are based on business modelling. So I looked at those today. There's not only the web services atomic transaction standards, but they're part of the WS transaction standard, and there is WS compensation. So there's a compensation mechanism built into the WS standards, and the business activity standards. And I don't know how widely any of those are implemented. I did a search to see if I could find someone saying, hey, we've done this particular standard, and I found lots of references to the standards, but no one's saying, you know, our business activity modelling is based on this. You know, perhaps it's there, they're just not advertising it. But we'll talk more about web services and the running out of puff in a future lecture. So in those types of business integration models, you tend to have atomic pieces, nice ACID pieces, and then join them together with distributed transactions with some support for what I'll be talking about next, which will be compensation. There are a number of what are called extended transaction models. Sagas is an older one of these, it's the next slide, and they're based on compensation. Compensation is, well, we did the wrong thing, but we'll fix up our mistakes and continue on. When I was actively working, researching in this area, it was notable how many times you think, we've got this situation, how do we resolve it? And the answer was, there was a long existing business process to handle just this issue. So the problems we're talking about here are not new problems. People have been integrating business systems for 1,000 or so years. And the problems are to do with integrating business systems, not with the computing technology. So there are solutions out there. It's called invoices and reconciliation. And so often when you think, I don't know how to do this, you will find there's a paper-based system that will do exactly what you want. because someone had this problem 500 years ago and solved it. So if you think about that whole purchasing model where you ask for quotes, and the quote is a binding contract for supply with a particular timeout period on it, etc. And when you start trying to emulate that, think, what I want is a quote, because the business process you want is the same, except that someone did it once on a piece of paper, now it's electronic, and the next stage of that would be a purchase order, which has its own legal implications. So a lot of these processes are there. They're paper processes, we're just transporting them. And the problems with these extended transaction models are exactly the ones that people have been facing up to for hundreds of years. So compensation, something goes wrong, well, we have a compensator. We work out how to undo it. It might involve sending things by letters to people saying, we've got to back out of that, or I can't meet this contract, but the mechanisms are there. I was doing some reading today, seeing if I wanted to talk more about that last topic there, eventual consistency, and which I will do in a future lecture. I'll tidy it up into the webby bit towards the end. And there someone was talking, one of the guys from Berkeley was talking about the consistency models and what happens if you're a bank with ATMs and you lose your network link. Do you want to say the ATM is down, or do you want to say we have a pre-established mechanism for getting money back from people? So if we give them more money than they're allowed to have, we can claw it back. It's okay. So perhaps we value servicing the customer more than we can't be guaranteed we won't, under some circumstances, give money out from an account that we shouldn't have. And there'll be bounds on that as well. But so, yeah, there's paper manual systems there which will often act as backup. The last one of these is eventual consistency, and I'll be talking more about that. It's the champion of this, as far as I know, is a guy I used to see at workshops and things, sitting at the edge of the room with his laptop plugged into the mains, hacking away. And he's now Chief Technology Officer for Amazon. So he was just this sort of geeky guy hanging there, and he seemed to have done well for himself. But Amazon, being the type of organisation they have, this problem, they've got lots of bits of code and they've got geographically distributed, and at the same time they want to have a consistent image of what their data is. And it's hard to do that in the face of network failures and node failures. So this idea of eventual consistency comes out of that, where, well, it may not be consistent now because we've lost parts of the network's been partitioned, but eventually it will all come up to be consistent again. So, and we can live with that. So we'll talk more about that later. The other odd person whose name came up in some of the reading on this was some bloke called Alan Fekete as well. His name was on some of the papers. So, sagas. And this is the type of model that your average business process automation thing will have buried into it. So we're going to talk about, first of all, it's only going to handle atomicity. It doesn't handle isolation. Atomicity is important. So we've got a long process, maybe inside one system, might distribute it, doesn't matter. And we're going to break it up into a series of smaller acid lumps, operations. And for each one of those, we'll define a compensator. And a compensator is simply a piece of code that we run that undoes something. So if we do whatever the action T1 is, then T1 inverse undoes T1. If we took goods off the shelf, then the compensation is putting them back on the shelf. So we've taken a long business process, we've split it up into a series of pieces, and obviously it doesn't have to be linear, it could have forks in it representing ifs and things. And then for each one of those we have a compensator, and if we get a failure, so here T3 has failed for some reason. It might be a logic failure, it might be that it found that the goods weren't on the shelf and it couldn't fulfill the order. And what you do is that, because that's an atomic piece, it can just abort, everything gets rolled back, and then we, okay. And then, I don't know what happened to the rest of that slide, then we simply, it's over here. So T3 fails, so then we automatically run T2 inverse and then T1 inverse. So we back out a lot of it by running the compensators in reverse order of execution. So we run T1, T2, fail in T3, we run T2 inverse, T1 inverse. I'm sure I had a copy of that slide with the other one in the next row under it, but perhaps. So the problem is there's no isolation, so things happen. It does avoid the problem, though, of trying to keep long duration locks and locks across trust boundaries and people keeping locks locked they shouldn't have. But as soon as you do a commit on one of those individual pieces, because there's no isolation, your changes are visible to the rest of the world. And data that you have committed is now visible to someone else. They could use it, but you could then run a compensator on your changes and something else has already made use of your committed data, which has now been rolled back, and you don't know about that. So that's a problem. It also assumes that compensators will always work. And that can also be a problem because as you don't have isolation, compensation can be hard to do it correctly. If you say, I want to undo this, but the assumptions your piece of code was based on at the time it executed don't hold anymore because someone concurrently has done something else. So compensators could be hard to write. There's a reference to a paper there, that's the DOI for it, which has got a really catchy title. It says, compensation is not enough. And that's probably my highest cited paper. So the authors are me and Alan and a few others, and it obviously struck a chord. It's got about 110 citations on just now. It's a pretty highly cited paper. And it's just pointing out that compensation is not enough. If you want to do these distributed systems, you need more than compensation, and compensation is hard to do. And I hope it's a readable paper. We wrote it some time ago, but okay, business transactions. We're now using the word transaction fairly lightly. There's a whole swag of business automation tools. So BizTalk servers, a Microsoft one, the BPEL was a standards group that was in this space. There's any number of commercial products from lots of people. IBM have things. And there's a standard there, WSBA, Business Activity Standard, and they're all tools that let you go and build these distributed pieces out of lumps and design it so that the business analyst can do the system design. You don't need a techie programmer, someone who just knows how to put Lego blocks together can do it. You draw the thing in a little box here and it's that, and then you draw an arrow to this one, and then you have a little diamond saying there's an if statement here. So orchestration of business processes in a way which is understandable. And they always have support for compensation. That's the way they're built. That's their idea of doing transactionals. And you'll have defined transaction scopes in their system, and they'll automatically invoke compensation if that particular transactional scope fails. And yeah, they're very sophisticated. So we're wrapping up this area now. So at the end of this particular talk, so we're going to use ACID for local, well-behaved bits because it's got really good properties. It's a lovely, simple, elegant framework, and it makes a lot of otherwise quite intractable problems just vanish. You'll get new problems, you'll get deadlocks, and you might get other locking-based errors, and you might fail to make progress, and you might get slow performance, but other difficult problems just won't be there because of the automatic atomicity and isolation. And only applicable in an environment with trust and low latency and appropriate system design. Otherwise, you're going to probably base something on compensation. So long-running transactions will be based on compensation mechanisms, and there you can cross trust boundaries because you're responsible for your own stuff and you trust your own stuff. And if someone you're talking to fails, then you can invoke your compensator to undo that part of the transaction. But maybe hard to do. And in a few lectures' time, I haven't quite decided exactly when yet, we'll talk more about when you're building systems on that web scale and how you might try to get consistency there, and about advanced consistency models like eventually consistent systems. Last bit of this thing, in the lab you used transactions in .NET WCF, and I thought I'd just show you some of that. And you decorate your code with attributes because that's the standard way you do things in that world. It's also in the Java world as well. You don't functionally, you don't come into a method and then call something and say, hey, I want to start something here. You decorate it saying, I'm transactional, and magic happens. And you have transactional flow, which means this piece of code must be in a transaction. It's allowed to be in a transaction or it's not allowed to be in a transaction. And there's a transactional flow protocol tied in with that. And that says when we're propagating transactions. So I said I want to be in a transaction. I need to tell my resource manager that about the transaction so it can do its stuff inside my same transaction, inside the same transactional context. And I want to perhaps call another piece of code and it says I want to be part of your transaction. We need to flow the transactional context around. And it supports two protocols for doing that. We need a protocol for transactional flow, and it supports WSAT, the web services way of doing it, which has a chance of working with arbitrary web services supporting bits of code. And it has the Microsoft proprietary model called OLE transactions. And don't worry about the name, it's just OLE transactions, and that's the native internal Microsoft way of doing it. So SQL Server will speak OLE transactions, and sort of probably will Oracle. I say sort of probably because we're not going to be talking directly to an Oracle database. We'll talk to something which is a driver sitting in front of the Oracle database, and it will do the protocol translation for us. So there'll be some in the Oracle remote access protocol. If you've got Oracle sitting on a server somewhere, then there'll be a way of doing transactional propagation in their protocol, and we will something will take the OLE protocol and translate it dynamically on the fly because they're going to be equivalent protocols. So you can enlist the Oracle resource in an OLE transaction-based system. It's just protocol translation. But when you look at, you'll see that you have a choice here of which of those two protocols you want. And in your example, you probably use OLE transactions. The service behavior is where you're specifying the ACID property, the isolation level we talked about last time, whether you want full serialization or be able to read committed data. That's a parameter there. And a transaction timeout, where you say, I want you to do something with this transaction, but by the way, the transaction cannot last longer than 30 seconds because this is a guard against rogue, runaway transactions. Transactions have locks. You can't afford to have the lock held forever. So that's what the transaction timeout. 30 seconds is probably pretty common. And operation behavior for each individual operation, whether you're you need to have explicit. So when I get to the end of the method, if it successfully completes, if the method doesn't fail, do I automatically say commit? So I'm turning the commit abort decision is method successfully completed or gave an exception. So I just don't need to write the code for that. So all of these properties are also possible to set via config files, which is the better way of doing it in many ways. So let's look at that next page. This should look familiar from the stuff you were doing in the lab last week. There's the top, there's a service contract for iCalculator and the operation contract for add. Says transaction flow option mandatory, so add has to be called within a transaction. And the subtract can be called within a transaction. So there's those options. Find another bit of code. There's the actual implementation over here. This service, the calculator service, the isolation level I'm asking for is full serialization. So when these transactional methods are calling into a resource manager, they're telling the resource manager full serializable is what I want. So that's propagating it down to the resource managers. And the maximum time I can be in one of these is 45 seconds. If I run for longer than 45 seconds, that method gets killed and the transaction gets aborted. The add here says transaction scope required. It needs to be within a transactional scope. It has to have been called from within something which is transactional. Then I said most of this stuff can be set by config. This will be in the app.config files, and the calculator service we've got, trying to find this what I want, the binding transaction flow true and transaction protocol is allow transactions. So this code, the code itself shouldn't be saying what the protocol being used in the system is. That's a config question. And that's basically that complete bit of code. The interface definition, the methods, and the appropriate bits of config. Yeah.
What is the serializable isolation level? Sorry, I didn't quite catch that.
Which one?
The isolation level.
Oh, so last week I talked about when you're asking for
network trans.
yeah, so part of the SQL standards, our resource manager basically, is how isolated do you want your isolation to be? And I thought, that's a good thing. I had thought about talking about that when I was on the train coming here. That all the good stuff I've been talking about happens when you have isolation level equals serializable. That's the SQL standard word, serializable, with a Z because it's American. But historically, a lot of resource managers have tried to dissuade people from doing that because it's more expensive. So with serializable, you have to get, assuming you're doing locking and not doing the Oracle mechanism I talked about last time, then you implement serializable by getting read locks on every bit of data you read. Read locks are shareable, so multiple people can lock them, but you can't convert a read lock into a write lock. So you're guaranteed that if you read a whole lot of stuff, no one will have altered those values you've read because you've got them locked. And in order to alter them, they would have to get a write lock on that item, and you have a read lock on it, and you're blocking it. When you get to the end of transaction, then you release all your locks, and people can grab them again. So it's more expensive because you're getting all these read locks. And I suspect the reason that historically people tended to use a looser level of isolation, read committed, is because the same reason that people tried doing page level locking, and the locks was just seen as being too expensive. Machines weren't fast enough. So the tests we were doing when we were working in this space, when Ian and I were working in this space, there wasn't much difference in performance even 15 years ago between read committed and full isolation. But historically people often do read committed because it's just tradition. But it doesn't give you full isolation. So there's lots of nasty corner edge cases. And one of the papers I was looking at when I was thinking about eventual consistency and consistency models, saying, well, some of the problems you come up with when you have one of these what's called partitionable system, where you can have a network break and you want to have a consistent view of the data everywhere, is exactly the same problems you have if you allow read committed. So people have been happy living with some of these problems for decades, so now we should say perhaps they're livable with, depending on, yeah, we'll talk about that later. Okay, that's the end of that one. Let me kill this and go to here. I didn't include anything from James. I cut that out. Okay. Performance. So I said this is one of two performancey things. This one's going to be the more general one, talking about what we mean by performance, things that influence performance, etc., and some fundamental performance calculations. I brought this in with me. This is a really important tool. This is the back of an envelope. You've heard the phrase back of the envelope calculation? This is an envelope. And incredibly useful. A back of the envelope calculation is you just doing a rough calculation. And that's probably good enough for most purposes. I remember I had a programmer working for us who was working with one of our statisticians, and he said, oh, I've got this thing in the great, okay, so it's taking 10 seconds per whatever to do this. And now I want to scale up to that. Let me just grab this 10 seconds, you've got this, that scales with the square of that. That's going to take you 25 years to run. Oh, and if you make it 5 seconds instead of 10 seconds, doesn't matter. So the back of the envelope calculations, those general feasibility questions are really, really worth asking. So, prop. And I do it all the time. You just, what's this going to be? That's roughly that. This is roughly that. What's the scaling like? Is that feasible or not? Is this going to take an hour, or is it going to take a month to run? And so rough calculations can be very useful. And then what Alan will talk about is more formal performance modelling. There's a mathematical area called queuing theory, and there is a whole lot of useful stuff in queuing theory space, because a lot of these systems can be represented and modelled using queuing theory. Now, you've all heard, an aside, so you all know about OO programming, right? The very first OO programming language, which wasn't called an OO programming language because they didn't know they'd invented it, was a language called Simula 67. Came out of Scandinavia somewhere. And obviously it was the 1967 version of the language. That's what 67 means. So Simula 67. And it was effectively the first OO programming language. And it followed on from an earlier language called Simula, and they did a second version in 67. But the Simula in Simula is from simulation. And what they wanted to do was do simulations of things like shops and manufacturing processes and computer systems. And, well, gee, I want to simulate the checkout. So they thought, we want to be able to create a checkout thing. They didn't know to call them objects, but they created checkout objects. And you could instantiate multiple ones of them, and inside the checkout object, you could have a queue feeding it of customers, and you could have, say, model the customer, and the customer could have a distribution of things they wanted to do, and so you could actually model that whole system. But they did it using what a few years later were called objects. But that was the very first simulation system. And so if you're being really serious, you can go and use simulation tools, and there's a lot of them, the simulation languages, to model any computer system as well, because they're mostly modelable. But to do it, you need to know the characteristics, statistical characteristics of the behaviour of your components, your requests, etc. But we'll talk a bit about some of that today, and Alan will talk more about it after Easter. So I'm away tramping through Central Australia. So Alan's doing that week. So, performance. So, what do we mean by performance? Well, how well our system's working, really. It's a vague word. So, we've got a workload. That's one good concept. Workload. And that workload consists of, here they're called jobs or tasks, whatever you want. So you take a workload that's composed of individual tasks or jobs, and each one of those uses a set of resources in a particular way. And one way of measuring performance would be, how much of this can I do? So we've got a workload, and then we're going to try to process that workload. Our workload will normally consist of not just one type of thing. There might be multiple types of jobs. In the database workloads, you tend to describe small, lightweight things and medium weight things and really heavyweight things. So we've got three here. A small, lightweight operation just as a read of one thing, quick bump, there you go. It might take a millisecond to run. The larger ones might be doing a more significant lookup and might be looking at hundreds or thousands of records and coalescing them. And then you have ones that do updates, and they might be much, much more expensive. I'll put up a different version of these slides later, and I'll put an extra couple of graphs in there, because I did have some from a previous version of this course where I looked at looking at a contention for resources and the effect, but I realised it also has a really nice thing of, I've got lightweight transactions and medium weight transactions in that transaction mix, so it's nice to see how much time each of them takes. So I'll put that up later. And if we want to describe our workload, we can say, well, our workload consists of 70% type A, 20% type B, and 10% type C. So if you're trying to model in some way your system, the first thing you need to know is what the workload is, because you can't model it unless you know what the load is. So one thing to do. An equivalent way of... Okay, I could do that and say, here's a file, go and, it consists of all these things, and you have some process which reads the file and spawns them off. That's a very atypical way of doing it. Normally what I do is have client systems that are generating this workload dynamically. And if I have that, multi-threaded client system, multi-system clients, then I will generate the workload there by waiting for a while and doing something. I'll be generating requests at a certain rate, but if I know the arrival rate of each piece of work, that's exactly the same thing as knowing that if I said 70% is this, if I want to re-specify that in terms of the rate of generation of requests, I've got to sort of invert that problem. So I can specify it either way, but later on I'll be mostly talking about generating them once every 10 seconds or once every 5 seconds or whatever I'm doing, but it's equivalent to any other way of specifying that same workload. If I'm describing a system, there are two fundamental types of systems I would want to model. This is all about modelling, even if the model is something written on the back of a piece of paper. And there are two types of systems, open and closed. In an open system, something out there is generating requests. That's it. The World Wide Web is generating requests. There's an unbounded, potentially, number of customers out there, all of whom are just generating requests. So if I was modelling a web type system, that's inherently that type of system. No. The other type of system is a closed system, where I've got a number of clients, and those clients are generating tasks. They're waiting for the task to complete and generating their next task, perhaps with a delay between receiving the response. And that delay is called think time. So that's the technical word for it. So you send a request off, you wait for the response, you get the response, you wait for the think time, and then you send off the next request. And it's modelling a human operator. You've got someone there who's hit the thing, wait for a response, look what the response said, do what the next thing, boom. That's what you're modelling there. But it's closed in that there is a fixed number of these client sources. And that's a very sensible model for systems which are like that, where you have a bounded number of requesters out there. This is a potential. The workload generated from such a closed system is potentially bounded, which probably means nothing at all to you. The alternative to being potentially bounded is potentially unbounded. Potentially unbounded means there could be an indeterminate and large amount of workload. So if I take my system, PC here, and I put it on the open internet and I run some application, and all of a sudden it becomes really popular, the amount of workload that the whole internet can generate is unbounded. There might be 1 billion people out there who might all of a sudden now decide to have a look at my system. The actual workload is unknown and unbounded. And I have to worry about that, because being unbounded is very dangerous for my system health. Whereas the closed system is bounded, meaning that there's a feedback loop there. The maximum number of requests I can have in my system at once is the number of clients I have. And if the system is slow, then the requests take longer to get back to the user, to the requester, and it takes them longer to send the next one because they've had to wait longer. So the think time may not vary, but everything is slowed down. So there's a negative feedback loop in there. So these closed systems have an upper limit on the workload, but the open systems don't have an upper limit on the workload. So we have to worry about how to control that workload. Measures, we've talked about this before, we mentioned these words. The throughput is one common measurement. You've got to have a metric. You've got to say what you're going to measure. So throughput is the amount of work we can get done in a given time, the tasks completed per minute. And we could either measure this at the server side, it's probably a sensible thing to do, or we could go and, if we had access to client systems, we could add up how many each of us do. We'll probably measure it at the server. Response time, a really useful measurement because it controls. So throughput is more concerned with how much money we're spending on providing the service. Response time is how happy our customers are. So I can improve throughput and at the expense of making my customers less happy. Measure it at the client. You could measure it from the time the request arrives at the server to the time the response is going out. If you do that, you haven't included the network latency and other overhead. So depending on what you want to model, you can model it either place. And sometimes you get back multiple responses to a request, in which case the very first bit of data that comes back is what you'd normally measure. If you were doing benchmarks on here, you'd say the first response is what I'm going to count. A figure of merit. So if I'm interested in performance, why I'm interested in performance? One, I want to make sure my system can cope with the workload. That's good. And I want to perhaps optimize performance in some way. I want to optimize something. Customer satisfaction, cost, whatever. So I need some way of what numbers am I going to get, because I can't optimize something unless I know what I'm measuring. So lots of things I could choose to try to optimize. And whether I want high or low ones there is a matter of choice. Now, good throughput is a high throughput, perhaps, but good response time is a low one. That's fine. But I might be getting good throughput at the expense of good response time, and we'll talk about that. And saturated systems are particularly bad at this. Look at this. This system is so efficient. I'm running it at 90% capacity all the time, and the throughput's really, really okay, but I'm achieving that good throughput at the expense of variations in the latency, the response time. So it's not the average response time still might look okay. I've gone from half a second, and as the throughput went up, as the load went up, I've gone half a second, 1 second, and I might be stabilising at about 2 seconds. And you think, oh, that's good. I've got good throughput, highly utilised system, so reducing my cost, and I've got 2 second latency. And that's fine. I'm happy with 2 seconds. But if you dig into it, you find it's 2 seconds peaking up to 10 seconds or 20 seconds. Of course, the system is overloaded. And your customers don't care about the 2 seconds average latency. They worry about the 10 seconds or the 20 seconds they've got to wait. So your variation in response time is another metric you need to care about. I did try finding, I've got a whole lot of graphs on this that I did back in 2005, because I was interested in trying to understand better this type of throughput and system measurements, and puzzling over the same thing. It goes up and then it sort of levels off, and it's okay. So what's happening here? And the answer was that when you hit that good utilisation level, your actual variation went out because of things went chaotic. You no longer had a nice, well-behaved, predictable system. You had a chaotic system when you got that resource too heavily used. But if you just looked at average response time, that wasn't visible. And if you just looked at throughput, that wasn't visible. They just appeared to go asymptotic, lovely. They went up and then curved over. That's cool. But what was happening in that curved over area, you're getting more and more and more chaotic because of reasons I'll talk about next. This is some boring stuff which people always get wrong, so it's worth doing. So, you're measuring something. Include the units. Silly, isn't it? Include the units. And this is Alan's bit here saying, if we're measuring storage, we talk K normally means 1024. And in the lab exercise tonight, to get the correct answers, you need to use K equals 1024. And don't get confused between bytes and bits. Dimensions, if you've done physics, you know all about dimensions. And this is in furlongs per fortnight, and we can convert from that to this, but the dimensions are really important. And dimensional stability is right. If you're measuring something and the answer should be in distance over time, then you better make sure that it is distance over time. So, now, that was the easy stuff. There's a difference between the number of digits you will get in a calculation and the actual significance of those digits. The resolution in a number and the number of digits you'll have in your calculation are not the same. And when I ran this course previously, this was always a point with students. You tell them and they go, I measured this thing and it was a floating point number, double precision floating point number, and it's got 18 digits. Boom, there you go. It was 0.1 blah, 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 blah. By the way, the timer you're using to measure that ticks over 100 times a second. It's not accurate to more than 0.01 of a second. So you can't give me 18 digits of accuracy here because you don't have it. So you need to understand when I get a timing thing, how much information is there, not when I print it, how many digits does it give me, because most of those digits will be nonsense. And we'll talk more about that. So, example I'm using here, now you're doing some time calculations and magically the system gives you, the framework gives you a number as a double precision floating point number, and when you print that out, if you don't tell it not to, it'll give you 18, 24 digits, but it's based on a 10 millisecond counter. So all those digits past the 10 milliseconds are nonsense. They're just calculation things. You divided, instead of being a third of a second is 0.3333. Yes. And perhaps you keep those around to multiply with each other and things and add them up, but at the end you've got to say my performance is this, and by the way it's based on a 10 millisecond timer, and that's all the information I have there. People are very fond of generating averages. I'm adopting this saying from a biologist I know in WA who says PCR is evil. Averages are evil. They're a terrible statistic, which is why politicians like them so much. And they're evil because they hide what's happening. You know, do I have, the average for this is 5. I've got two samples, one is 0 and one is 10. Is that meaningful? You really need to know information about the variance. So, and that last thing there with the Greek letters is if you're doing job type A and job type B and job type C mixed in all together, and you want to talk about the average response time, then you've got to do weighted averages. It's that simple formula. So sometimes you need to do weighted averages. And then you're probably going to want to do if you're interested in how my performance varies in some way, how does it vary with the amount of work to be done, how does it vary with the resources I allocate to it, then you'll probably want to plot them. That's all cool. Do a simple plot. And often, if we're trying to optimize performance, we might say, we want maximum throughput with a bounded level on response time. And if you do that and you accidentally overloading, you'll get really high variance. So you shouldn't be saying, I want to maximize throughput, so I'm optimizing the utilization of a system. So I think, okay, I want an average transaction time of 1 second, and then I want to ramp up the workload to the maximum number of requests going through the system while maintaining an average transaction time of 1 second. And if you do that, then you think, oh, I can just keep on increasing it, but what you're not looking at is the bounds on that average. So if you're doing that sensibly, you should say, I'm not interested in the average, I'm interested in the 99%. That 99% of my transactions complete in this time plus or minus something or other. I need to look at the bounds of it. So you might talk about the standard deviation of that average. Just talking about an average by itself can be very misleading. There's 2 from the book, which is referenced at the end. So I've done charts like that many times. So if I was to do some system, and in fact, there you go. I'll come back to that slide. This is a REN, but this is real. So this is performance measurements I did for one of my tools that I've written, and this axis is the number of concurrent processor cores actually. It's a 24-core machine, and I'm not using the hyper-threaded threads, I'm just going from 1 to 24, so when it's up at the end there, it's got 24 cores running, and I run it with 5 threads and see how many reads per second. Reads per second is my performance measure. I've got a huge file of billions of things, and I want to process it. So reads, and the file is made up of things called reads. So how many reads per second is my performance metric. So with 5 concurrent threads, I can do 150,000 a second. And then if I double it, I get 300,000, which is good. And as you can see, as I'm increasing the number of threads, it's pretty close to linear. And linear is what you want. Now we'll go back to the previous slide in a second. To get that is probably about a year's work overall. I've probably spent a year of time total on that program over 5 or 6 years to get it like that. To get it to scale that well was incredibly hard work, because what it's doing is taking each one of these reads, think of it as a string, chopping it up into small bits and dropping those small bits into hash tables. Because what the whole job is to take the file of 1 billion reads, and I take the first small substring and then move on to the next small substring, and I want to count the number of distinct substrings in there. And you're talking about billions of them, so that's what I'm trying to do. So it's basically just, when I last wrote this up, I said, the algorithm here is incredibly trivial. It says, get the next substring, drop it into a hash table, if it's not there already. If it is there already, increment the counter. That's it. That's the algorithm. Except it's got to be able to do it at that scale. And so to do that, it's got shared hash tables. They're lock-free hash tables, because I'm worrying about consistency and not losing updates, because if 2 threads are incrementing the same thing, then there's a clash there and I could lose counts. So they're thread-safe hash tables. Had to worry about that. There are, because of the way the algorithm really is, it's filling up tables, and when those tables get filled, it throws them out to disk file asynchronously. So the counting threads and the writing threads are separate to each other. And it's writing out to a solid-state disk, a very fast solid-state disk, to avoid some of those overheads. So background asynchronous I/O everywhere. When a table becomes full, the thread which filled the table queues it for writing, and then swaps in an empty table over the top of it, so that then the other concurrent threads can keep on adding into that table. So I'm doing buffer swapping dynamically as well. And all of that complication is necessary to get that more or less linear. And if I don't do that, it's not at all linear. I can get that going like a horizontal line if I didn't do this. It'd be almost a horizontal line rather than a nice diagonal line. So getting good scalability is bloody hard work. Now let's go back to that previous slide, because there we go, on the top corner there. In this case, we've got transactions per second, reads per second is the equivalent, number of CPUs, and you see that that piece of code was basically pretty close to the ideal, but what we normally see, isn't a laser pointer here, is there? No. Okay. What we normally see is those things flatten out. We start off tracing the diagonal, and then we curve. And that curving is because of resource contention of some form. It could be waiting on locks, it could be all the other resource contention I'll talk about next, but is resource contention. If you have no resource contention, you'll be on that diagonal line. And when I was talking before about, we say we're measuring throughput, that's a throughput measure. When we start curving off the diagonal, we're getting delays in our system, and the longer I'm waiting for resources, and the longer I have to wait for resources sometimes, that will be reflected directly in the variance in that response time. So when I start deviating off that diagonal there, then I'm going to be getting more and more variance in my response time measure. So just saying, oh, well, I might as well go out to here because I picked up an extra 20% throughput. I may have picked up that 20% throughput at the expense of making the variance that much for that response time figure to that much. So, but the average might still be the same. In fact, what tends to happen really, if you measure these things on a typical system, is you go up and then you start going down again. And when you're going down again, things are really bad. And that's because then you're constantly waiting for resource access. So if you're deviating from those ideals, it's because you have resource contention and queuing, which I'll talk about next. And remember, averages are evil. There's that slide we just had. Measuring performance. Being good computer scientists, you will want to measure your performance. That's easy. Measuring performance is really good. I do it all the time. Because I write a bit of code and I think, I wonder if this is working fast enough, or I want to trial one way of doing something versus another way in code. And I'm going to be doing it a billion times, so I care. So I will go and do little performance studies on it. And lots of these are throwaway code, which are performance studies. And so I need to measure time. There is a system clock running on the system. And that might be, if we've got an N gigahertz processor, it might be that clock. That clock these days is probably really unreliable because we're constantly changing the processor speed to reduce power or to give us a boost when we've got some thermal headroom on the processor. So it won't be the actual instruction clock. But we'll have some type of clock in there which is going tick, 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 tick. And that's going to be used for some of the interrupt handling, I/O, do this and come back in 10 milliseconds to check the results. So the operating system needs to have some way of scheduling events in time. And the actual processor scheduling, there's a bit of the operating system, the scheduler, because you say, here my program wants to run, And if the processor is busy doing something else just now, it puts it onto a processor queue, and running tasks get a time slice. It might get run for 50 milliseconds, and the operating system goes, oh, time's up. So that system clock is used for all those internal operating system mechanisms. And it probably isn't that accurate. You know, for the operating system being woken up every 10 milliseconds to say, should I do some housekeeping or swap something, that's good enough. Because if I was to make that a microsecond, then the operating system's being woken up every microsecond, and we won't do anything apart from checking to see whether I should do something now. So there's this balance between frequent time, very fine clock here, and getting things done. So in the order of a millisecond or so, millisecond, 10 milliseconds, perhaps higher. There is a wall clock of some form. You expect the computer to know what time of day it is. Okay, there's a clock for that. That's probably based on that system clock. So one of the things the operating system will do every time it gets one of those system clock interrupts will be to increment the time of day clock. Oh, it's 10 milliseconds later than it was last time I was here. And it's approximately 10 milliseconds, that's okay. And then real processors, sensible systems, have specialised performance counters, timers, whatever you want to call them. Because performance measurement is so critical that there's actual hardware level support for this. These are high precision counting registers, basically. They're timers in the sense that a timer is just a counter. So I will have a clock somewhere buried in the hardware which is ticking over, say, once every nanosecond. A little high precision quartz crystal clock thing ticking over, and that increments a timing register once every nanosecond. And how many nanoseconds is 2 to the 64 nanoseconds? Big number still. So we can, longer than the uptime of the machine will be. So I can implement these clocks simply by having a little timer circuit which is highly accurate, because I can make that, and all that I do is just increment a counter. And then in order to read the clock, I just read the value of that register. That's it. And those timers exist. On multi-core, multi-processor machines, there's some interesting quirks there, because I might start one of these timers going on one processor core, or one processor in a multi-processor system, multi-chip system, and then pick it up again somewhere else. So there's got to be some coordination. And I've had systems that didn't do that well, so you get odd results. But mostly these days, the very lowest level of the system architecture takes care of coordinating these high-performance counters at that level as well, because they're important. So, two things, precision and resolution. So, how is the value being reported to you? Is it being reported to you in clock ticks, which is what most of you will get? Or is someone translating the clock ticks into nanoseconds or microseconds? That's one question, the precision being given back to you. But the more important question is the resolution there. So precision and resolution are not the same thing. So the resolution is the important thing. That's what's the information content in that. So you might get something saying, you might get a performance counter which says, I'm giving you an answer in nanoseconds, but by the way, I'm only incrementing the clock every 10 milliseconds. So just remember what that is. So many timers have deceptively high precision, but quite coarse resolution. And be aware of that. There's a Java slide here because it was here and some of you were interested in it. It's interesting up the top there because we've got the Unix-based systems. This is the system clock I was talking about. You can get it from current time in millis. It's a time in milliseconds. And the resolution, if you're running on Linux or Mac OS, then it's a millisecond. If you're running on modern Windows, it's 10 milliseconds. So that's the resolution of that timer. And there is a thing called System NanoTime, which is the best precision timer available, but no guarantees. There is an Oracle Java package called Flight Recorder, which is a performance measurement package, but it's not available in the free JDKs. It's in their commercial packages. And people go and write, if they're running on Windows, for example, they can access the system high performance timers, so they write a bit of Java wrapper stuff and, hey, now I can go and use those. But it obviously only works on a platform which you can do that on. The .NET code is this type of stuff. I converted to using this. I used to use the Windows calls, and then they brought in stopwatch. There's a function in system.diagnostics called stopwatch. You grab a stopwatch object, you do stopwatch start, it starts one of these high precision timers. You do stopwatch stop, and it stops the high precision timer. And what you've got now is the number of these clock ticks that happened between the time you did start and the time you did stop. If you want to know, if you want to convert that to a time, you then just go and call, there's a whole lot of these conversion functions, methods in the object as well. So that converts the time between those two calls here into a standard system time that you can manipulate and print out. And there is another call which gives you stopwatch.frequency and says, what's the actual resolution here? So how many ticks per second is this timer reflecting? And the answer will be 10 million or something, or 100 million. It depends on the hardware, but it's quite high. So that's perfectly reasonable code. So I write that type of code all the time because I'm interested in the behaviour of a piece of code. Yep, range intervals. If you're doing a measurement, you've done the measurement once, doesn't mean you understand how it varies. So you do it multiple times. I only did that example I had before 3 times because it probably takes about an hour to run. So it's a bit painful to run it multiple times. But I needed to run it multiple times to get an idea whether what normal is. And so measure it multiple times, and then you can use stats on it to work out how to interpret those numbers. Okay, so this is Alan's comment here. For a narrow range, you need to sample many executions and transactions. True. So if you want to get a good idea of the distribution, you want to know whether it's a normal distribution or whatever, then you need to do lots of things and measure them all and do the stats on it. But remember, when you get into that non-linear part of those curves, then you will be getting more and more variance. Recording data, yeah, you should record the stuff you've got. That's an interesting point. So, if you're trying to do performance on a multi-threaded program, that can be tricky. Because I've got counters, and even if it's just adding up time, I've got one of these tables containing all this stuff. I want to know if I want to work out the time for transactions A, well, I need to remember all the transaction A types and the total time, perhaps, and the number of time I did it. But if I'm doing this in a multi-threaded system, then that now becomes, if I'm updating this, I've got to lock that table because I'm about to update it. You've got to lock these things, in which case all my threads are now possibly single threading on that stats table. So what I normally do for that is I allocate one of those stats tables per thread, so they're all just working on their own copy, and then at the end of the program, I just merge all those tables under lock protection. So when the thread finishes, it says, okay, grab a lock on the shared table, copy, add my stuff into it. The locking only happens when they're finishing anyway. So it is a bit tricky when you're trying to do performance measurement on multi-threaded programs to not cause an additional source of contention. Don't measure your test harness, that's true. Keep metadata and document what you did. Yeah, it's really easy not to do. I've got some numbers, and you come back 6 months and go, what the hell did those numbers mean? What were the parameters I used when I did that run? It's a repeatable science, as they say. If you want to look at things on the way, there's a nice slide shot there saying of perfmon in Windows systems. I've used perfmon quite a lot. You can just use it as a pretty little graphing tool. You can write your own performance counter. You can create your own performance counter instances. So you can ask the performance monitor to keep track of something that you are counting by creating your own performance counter instances, and then perfmon will track it for you, along with many, many other things. I remember when Windows NT first came out and I went to a presentation on it, one of the Microsoft guys said, well, people complained we didn't have enough performance monitoring, so we decided to fix those complaints. If you run perfmon, there's just pages and pages of things, and you click on those and there's another 100 things you can monitor. It's just not quite over the top. And a huge collection of built-in counters. And the interesting thing about this example, I thought about replacing, because it's obviously old from the window layout, but the nice thing is these are DB2, IBM's database counters. So IBM, when they ported DB2 to Windows, just wrote the perfmon classes, and now perfmon is monitoring the IBM database because they just supplied the right classes. So you can tailor perfmon to meet your needs. And it looks pretty. Benchmarks. Benchmarks are also evil. So I said you've got a workload, and you're running your workload, and you're seeing how your system behaves. That's a benchmark. That workload is a benchmark workload. And there are many standard benchmarks available. Most of them are based on, theoretically, some type of useful real-world system that you're trying to model. Designing good benchmarks is hard, and there's an unfortunate tendency for people to pick on benchmarks that are favourable to what they're trying to show. It's like any other marketing tool. But there are a whole lot of them. These people, TPC, the transaction processing community were really into benchmarking at one stage, and there's Transaction Processing Council, because you had the likes of Oracle and IBM and Microsoft, etc., saying, we're doing the best transaction processing platforms, well, prove it. So they all got together and decided these are standard benchmarks you can run to talk about how well our particular transaction system and database, etc., work on the types of workloads you're interested in. So you can do comparative shopping of that, or you can work out price competitiveness or whatever. So these are a variety of TPC benchmarks. TPCC is basically obsolete. That's a data warehousing workbench. TPCE more or less replaces this. This got a bit gamed because computers got fast enough, storage got fast enough, memory got big enough that they became, how big a number do you want? Or just to throw the hardware at it. So TPCE was meant to be a bit more computationally challenging. The next line is some Java benchmarks that various people have done. And specialised one, there's one that models an eBay-like system called Rubus. And there's any number of them. YCSB is really a NoSQL database type benchmark done by Yahoo Research. So many, many benchmarks out there. Designing good benchmarks is a really hard task. And if you ever get involved in processor benchmarks, there's lots of standard processor benchmarks saying, my processor is faster than yours. They're really problematic and flawed. And gamed as well. So some of them are obsolete because the compiler optimization people said, we know how to make that benchmark run faster. We'll just do something. Benchmarks are tricky. So there you go, TPC. When you're running something like a standard benchmark, this is the type of system you're doing. You have client systems that are generating your workload. Each one of those will be running a script which says, choose what to do next, send it off, wait for the response, etc. They'll be running on individual machines or individual threads, and then it goes to the network, and we hit the server, and we do stuff. That's fine. The SUT is the standard word used there, system under test, and this can be arbitrarily complex. And obviously you want to run your clients on something other than your test system as well. And I've been involved in benchmarking like this. We've had to do it for government contracts, etc. Pretty standard. Oh, there we go. Right, now the more interesting stuff, resources, which is stuff that's tied into tonight's tute as well. So I've mentioned the word, there are lots of types of resources. When things start going slow, because you normally have contention of resources. So you've got processor, you've got I/O, whatever that means. It really means the I/O parts of the operating system, the physical buses that the I/O devices connect into, and the I/O devices themselves. That's I/O in general. But there's lots of bits in there, network of course. And each of those types of resources has different characteristics that are related to performance. And they're related, often related in that this is the inverse of that one. So, but you might choose to look at them differently. And it's really important to understand those characteristics, because you can't do the back of the envelope calculation unless you understand the characteristics of the resource you're dealing with. So the characteristics you're interested in often are the cost of preemption. So resource is busy doing task A, you want to pull it off task A and get to do task B, or it's just done something for task A, it's now got to do something for task B. What's the cost of that switch? Either interrupting what you're doing or going from doing something for task A to doing something for task B. And some devices have very low costs of preemption and some have quite high costs of preemption. Cost of over-allocation. What happens if I trying to get it to do, does it behave really well when it's lightly loaded, but really badly when it's heavily loaded? Some systems are like that. What are the latency characteristics? What's the distribution like of the latency characteristics of this device? Is there read caching? Is there write caching? I'll talk about those next. And do they support concurrent usage? So let's look quickly at the bottom here. So, processors. At some level, processors are really preemptible. You're running along for one bit of code, a timer interrupt happens, the operating system grabs control, throws you off, puts someone else on, and you continue on. Oh, so you think, great, really low cost of preemption. That was true in 1960, perhaps 1970. But as we make machines faster and faster, we now start caching things, and I'll talk a lot more about caches soon. So we've got all this system state related to task A, and we want to move to task B. That system state all needs to be re-established. So we may actually have quite a lot of preemption overhead, even though it doesn't look like it on the surface, but when you look down, it really is quite an expensive thing to do to preempt a task. So caches, cache conflicts, if I've got multi-core machines or multi-processor machines and I'm migrating processes around between them, then there's lots of cache implications of all that, and then also the overheads in the operating system for managing this preemption as well. So compared to some things, processor is really quite preemptible and there's fairly low cost. And I care about preemption because as my workload goes up, I'm achieving that workload on the processor by time slicing it. You have 5 milliseconds, you have 5 milliseconds, you have 5 milliseconds. And when it starts getting heavily loaded, then these factors start coming into play. Hard disks, spinning rust. They're the classic for cost of preemption. If I'm the only user of, if my task is the only user of this disk and I'm reading something sequentially, I move the heads physically. I've got to move heads, little linear motor, go rink, move the heads to the right spot. It's probably going to take about 5 milliseconds. It doesn't sound very long, but it does when you're talking about gigahertz clocks. So 5 milliseconds later, I'm over the right spot on the disk. And then the disk is spinning, so I've got to wait for it to come round. And then I can read. In tonight's lab, you'll do some calculations on that. So you've got head movement cost, rotational latency. You've got some type of, there's interface cards, there's operating system stack getting in and out of those. So you might have queues there. And there's caches to worry about. But these are really bad for preemption because I'm reading my file, which is just here, and then have to read someone else's. I've got to move the head, and that's another 5 or 10 milliseconds. Whereas if I didn't get preempted and I kept on reading the same file, I don't get the head movement costs. So it's very, very much faster for me to not share a hard disk. Hard disks preempt really badly, as you'll see in the lab. And solid-state disks, well, they don't have this. They're really good. 5 microseconds latency or something. That's cool. But there are caching issues around there and garbage collection costs, and they're not perfect either. So these work a lot better than these, but they're still not perfect. So go back to transactions in the more general sense. So each unit of work we're doing is going to take some resources. It's going to take processor time for the application, for the system services we're calling on, for the database, and that process time is going to be shared amongst all the competing processes which are ready. The transaction is going to do I/O, so it's going to need I/O time. That's largely going to be disk storage, reads and writes time, the actual time spent in the operating system queues and in the physical devices driving the disks isn't that bad. We will typically use, database systems will use caches to reduce that time a lot, particularly spinning rust ones. I had a slide in the previous one of these where I was talking about one of the TPCC benchmarks that IBM had submitted, and they had a machine with 2 terabytes of database cache just to reduce the I/O costs. And we've also got shared resources, memory tables, locks, whatever, and we have to wait for those. So these are all the factors that are going into our transaction. And if I was modelling these transactions, they're all the things I've got to model each one of. And the response time overall is going to vary with the heaviness. How much processor time do I need? How much I/O? What type of I/O is it? Is there contention for shared resources? The concurrency is our friend. Typically, we'll run multiple things at once. We do that because we can overlap things. So here's a job that uses some processor time. It does some I/O and then does some more processor. And it takes 3 units of time. And by overlapping them, by running them concurrently, then, well, this one's doing I/O, this one can use the processor, and vice versa. So we're going to get, we could do 1 job in 3 units of time, and we could do 2 jobs in 4 units. So it's obviously increasing the load in our system is increasing our system utilization. That's a good thing. But only good up to a point, and the more load I put on my system, the more those resource limitations I just talked about are going to impact on us. So the reason this is going up and then curving and curving down, is that's where all that contention, the resources which are not very preemptible friendly start being preempted. I'm moving the heads on a disk. I'm dirtying up the caches in the processor, and I've got to reload them from slow memory and things like that. There is a cost to preemption, and by trying to do more and more things at once, I'm pushing more and more of that sharing and the preemption that comes with that, and that's what's causing that curve to go down. So performance will start to degrade with more concurrent requests after you've reached that knee, and how badly depends on the nature of the resource. And you should be able to roughly calculate how much load you can handle with an individual resource, back of the envelope calculation, and that can give you an upper bound on what you can get through that particular resource. So in the lab you would say, okay, I've got a hard disk, spinning rust disk, and I can read from it at 250 megabytes a second, and I've got 5 milliseconds average latency. How long is it going to take me to read this? That's a good question to ask. And then I can replace it with something like solid state disk. So you get an idea of the maximum throughput of that system, of that resource. And a pretty common rule of thumb is you don't allocate things to more than 80%. Allocating to 100% is a fool's game. So 80%, 80% you aim for 80% CPU utilisation, you aim for 80% of anything. And that's just a rough rule of thumb. And I hope when Alan gets around to talking about queuing theory, you'll see where that 80% comes from. So it's just a reasonable thing. 70%, 80% is a good number. But remember they're averages, so you're going to be getting variance in those things. So that 20% unused is to cope with the variance in the request rate. So you will get an occasion of 100% utilisation, but if you fully allocate, then, well, I'll talk about next, you'll go to infinity. So you don't want to go to infinity.
80% is the target peak time, right?
Sorry?
80% is the target peak time, right? Anticipated peak time.
80% overall average utilisation. Because you want to give some headroom so that when you do get peaks, so obviously if you're saying I'm going to size a system for my Christmas retail rush, then that's that big, but the individual resources in there you're going to be scheduling 80% of their utilisation. So because you're getting a distribution, normal distribution of requests at any point in time, so sometimes you get more than others. So you want to give a bit of headroom for when you're getting that higher request rate, because the request rates are an average with a distribution. So you want a bit of headroom for that. And if you don't have that headroom, bad things can happen. Which comes to the next thing, bad thing. I said we had bounded systems and unbounded systems. And unbounded systems can go bad because the more workload you have, the less efficient things become because of all the reasons I just talked about. But there's no feedback loop there. There's an infinite number of people out there pushing things into my system, potentially, and they don't know about how busy I am. So they just keep on putting more work in, so my workload just keeps on going up, and the more it goes up, the less efficient it becomes, and that's a really bad feedback loop. That's a positive feedback loop, and you're in trouble. So if you have one of those unbounded systems, then you get what's called thrashing, where you basically don't make any progress at all. The classic one for thrashing is virtual memory thrashing. You over-allocate memory, and you touch some bit of memory and say, oh, sorry, got to get it off storage, bring it in. Oh, there's no room for it. I'll throw something else out. You drop it in. Oh, I need something else. And you spend every memory access is basically a disk access. And you get no work done on your system because you've over-allocated and you got to the point where there's no headroom. So thrashing is what can happen. And to solve that problem, you need to have some form of mission control which says, this much workload I can allow in, and beyond that point I can't allow any more work in. And what you probably do if it's potentially an unbounded system is refuse requests. And if you look at HTTP, the system has received your request and decided to throw it on the floor. Response. One of the HTTP responses is, system overloaded, we dropped it because of just this purpose. You look at the system, I can't handle any more requests, we're finished. And you'll get a nice message back. If you have a bounded system, then you can queue things, and I'll talk about queuing next. If you have a resource which is in use or fully allocated and a request comes for it, you can put it on a queue. And when the resource becomes available, something will be taken off the queue and the resource will be allocated to whatever it took off the queue. Queues are not magic. You can only use queues effectively if you have a bounded workload, because queues are a balancing mechanism, not a limiting mechanism. They're there because we have peaky requests and we want to sort of average them out. So we just use the queue as a buffer. But the actual resource is still bounded in its ability. You've driven along a road somewhere at a busy time and you're going on the highway at 100 and you hit 5k out of some town and there's a queue of cars all the way to the town. And you get through the town and you're back up to highway speed again. That's a queue. And the resource limit we have here is how many cars can go through the town at 50 kilometres an hour, and we can calculate that because we know what that is, and that's the capacity of that road, and potentially that queue can grow indefinitely because there's no feedback mechanism unless you get told on the radio that, by the way, don't try going through Mossvale, you won't be able to get through, and you go a different route, but that's an unbounded queue because the drivers along the road don't know what's coming up. So, and their arrival rate has got nothing to do with the capacity of the system. So queues are a great mechanism for levelling out peaks. So I'm busy just now, but I'll get round to you in 5 milliseconds or so. And so lots of queues in the system, they're everywhere in a system, and there's various queue mechanisms. First in, first out is a real queue, or we could have priority mechanisms. So the queues we have for allocating the processor, the scheduler queue, is often priority based, and we might do efficiency based queuing as well, selection as well. So I said we've got spinning Rust disks, we've got to move heads. Well, the queue we have of requests for the disk will probably be ordered by where we'll go and say which is the closest to where we are now to avoid moving the heads. But then you've got to worry about starvation and other complications there. But people are worried about all these things. And the reason we have admission control is to stop the queues growing out to infinity, because they will otherwise. So, but a closed system won't have that problem of going to infinity because it's got that inherent negative feedback loop. A waiting client can't issue another request. But open systems need to reject requests in order to, otherwise the queues will go to infinity. The distribution of your request is really important and should be understanding that. Yeah, that's a good point. So we've got a system where we've got jobs arriving exactly one every 1.3 seconds, and they take 1 second to run. We're there exactly. Then, of course, there's no queuing. Request arrives in the system. System's available. It runs it. System is idle for 0.3 of a second. Great. Now we say, okay, we've got arrivals of average of one every 1.3 seconds with some type of normal distribution with a standard deviation of something. So sometimes a request will arrive while there's still another request being processed, in which case we just drop it on a queue, and the queue will just sort of buffer things up for us a bit. We'll wait for that one to finish, and then so we might be delayed 0.3 of a second, and then we run it, and then we might be idle again, or something else might have arrived. So it's just evening out the requests and the buffering between the two. So that's all cool. So we even out the peaks in resource requests. But remember, we can never actually ever exceed the resource capacity, otherwise the queues will grow to infinity. In any system, there will be some resource which is your limiting resource. It's called the bottleneck. And you often need to know what that bottleneck is, because if you're trying to add resources to a system to improve overall performance, it's only worth adding resources to the resource which is the bottleneck. So if you're waiting on disk, then putting in more processors doesn't help you because you're waiting on disk. There's already spare processor. It's tied into a similar rule called Amdahl's law. Gene Amdahl was a computer engineer back in the 60s and 70s. IBM 360 chief architect, I think. And Amdahl's law says it's a parallel programming thing, and it says you've got a bit of sequential code and a bit of parallel code. As you keep on adding more and more parallelism into the parallel part of the code, eventually your whole system will run at the speed of your piece of serial code. The piece of serial code will be the dominant factor. So you can't just add more and more parallel threads and reduce the size, the time of your computation, because you hit the bottleneck, you hit the piece of serial code, and you can't. It doesn't matter if you went out to infinity with the parallel bits of code, it's not going to impact on the bottleneck, which is the piece of serial code you have. And that's when you start writing highly threaded code. That's a really important rule, because you think, I'll just do it. No, I'm sorry, that sequential bit of code there is your limiting piece of code. So happens in lots of places. So you have bottlenecks, and you might want to solve the bottleneck by adding more resources. And of course, typically when you add resources to a bottleneck, what happens? The bottleneck moves. All of a sudden the system doesn't become infinite in capacity. There's always some other resource which will now become the limiting factor. So good, you've moved the bottleneck. That's okay, you might have doubled your whatever performance by doing that, but there'll be another bottleneck. And going back to what we talked about a few weeks ago, stateful and stateless things, stateless resources are really quite easy to scale because state is my problem, and stateful resources are much harder to scale. A bit of an aside about caching. Caching if you're an American, which is why they spell it with a dollar. Caching if you're English speaker. It's a very famous, widespread example of trying to improve performance by effectively removing a bottleneck. And inside processors, there are many types of caches. There's level 1 cache, level 2 cache, level 3 cache, typically for a modern processor of different speeds. And there's a branch prediction mechanism which tries to say, where should I go when I get this if statement? I cache the results of those computations. So the next time round, I assume you're doing a loop, so I'll do the same as I did last time. There are sets of decoded instructions to save time here. Anything I think I could do, if I remembered the results of doing a computation before and use it again, I cache. There's caches everywhere. And then if I go up a level, the file system is full of caches. You think, I open a file and read it. Well, perhaps you read it an hour ago and it's still in memory. I read stuff. I read ahead just in case I happen to need it. There's caching in the file system. The database is full of caches. So caches everywhere. And caches, it's built on the opposite of queues really. Caches built on the idea that if I have something, some bits of it will be accessed really frequently and some bits will be accessed much more rarely. So I can afford to take the really heavily used stuff, the hotspots, and put them into something really fast. So if I'm going caching disk storage into memory, the memory is orders of magnitude faster than the disk storage. So I'm caching disk into memory. Memory's faster but a lot more expensive. In the processor, I'm caching slow main memory, which is the fast stuff as far as disk is concerned, but I'm caching it into really, really fast register type level SRAM rather than slow ordinary memory. And so I'm trying to find and magically hold hotspots from much larger data sets, the commonly used bits. Caching algorithms are always just this. I've got a request, I look in the cache, if it's present I return it, otherwise, assuming the cache isn't full, I'll find a victim, throw it out, the least recently used as a common algorithm, and load that from slow storage into the cache and then return the data. And then the next time I get a request for the same thing, reasonably soon after, I'll just be able to get it from the cache. So the effect is really effective, and typically also I'll load much larger chunks in a single request. So at a processor level, I may get a request for a 32-bit word, but what I'll load is 256 bits. I'll load a whole cache line, a whole memory chunk in, because I'm assuming there's also going to be locality. If you've read that thing, you likely want the next one as well. So I'm assuming there's going to be some sequentiality and some highly non-random access patterns. So that's caching. And for caching to work, the hit rate needs to be quite high, and you'll see that in the lab. And if it all works out, then the caching is incredibly effective. Caches are also used for writes, and they're used there to consolidate writes. So the database caches, I bring in a page, you want an individual record, there might be 100 records on this page, I'll bring in a whole page because you might want to read the page again, you might want to read the same record again, you might want to read another record in the same page, and when you're updating it, you update that one, and I'll leave it in there for a while in case you want to update something else in the same page. So I'm coalescing writes there. So they're all good things. And solid-state disks will use a very faster and more robust bit of its solid-state diskness as a cache as well. So, and I'll normally use memory buffering as well. So you say, here, write this to the solid-state disk, and it says, okay, done. It's lying. It first of all dropped it into a buffer and then returned, yes, it's okay. And then it moved it into a piece of faster storage, which is permanent, and then later on it will move it into its final home, because the moving into the final home is an expensive process. If I'm lucky, I can combine lots of them and do fewer of those operations. So caching is really good, but caching only works if we have high locality. Right, bringing it back to caching, back to architecture-y stuff. We also do caching architecturally. So in this system here, we've got something with sort of, that might be an EJB things, these might be entity beans. In this model, we've got a database here. This might be our entity layer there. And these are in-memory or at least local copies of bits of my database. And the application wants something, it goes and looks in, do I have a copy of this locally? If I don't, I go out to the database and bring it back into here, and next time I want it, it's local. So I'm bringing objects in from the database into my local memory or system. So I'm caching bits of the database there. And we talked about optimistic concurrency control, because obviously I might be caching the same objects into all of those caches, and someone updates one of them in one of them. How do I handle that? Which takes us back to the optimistic concurrency control we talked about, because I've got to sort those problems out. And if I can get the next slide, there we go. But that graph says it can be very effective. So here we've got well sub-millisecond, we've got 100 microsecond type time if we're getting it out of that local EJB cache. And if we we've got to go and that would be if it's in memory on the client system, that would be if it's in the cache, which could be in storage locally. This is if we've got to go out to a remote system. So quite a big performance difference there. 23 times faster. And typically, there are lots of caches. Cache in the database, app server have caches, which are caching bits in the database, the bits of cache in the web server layer, and when we go out to the internet, there's caches out there as well. So caches everywhere, and the browser. Right, I think I might be able to finish these off. I talked about adding resources. We've got a bottleneck, we add resources. What do I do when a resource is fully utilised? Well, the answer used to be one time I could scale up, put in a faster processor. We don't have faster processors anymore. Processors haven't got faster for a decade now. So we can't go faster. So we can scale out. We talked about that a few weeks ago. We just add more resources, boxes, and we can add them at any layer, which is really a good advantage of that layered architecture we saw before, because now we can say, oh, this is that layer. We can scale that out this way because it's got these characteristics. This layer has these characteristics. This was how I'd scale that particular layer. So the layering helps here, thinking about scale out. And if we're running stateless business logic, that's really easy to scale out. Database servers, state servers, they're a lot trickier for all the reasons we've talked about, and we'll talk more about that in a minute. So we just add more boxes. We've got to have some way of spreading the workload out across those boxes. That's called load balancing. And databases, well, partitioning or replication, I'll talk about that in a minute. And that's going to, those decisions are going to have impacts on the architecture and on management, of course, because we've now got a more complex system. But one nice side effect would be that as well as getting increased performance, we might also pick up increased robustness here as well. Because now I've got two boxes handling one load. Oh, I might be able to lose one of them. What happens if one of them dies? Ah, the other one's still there. Or what happens if I have 3 or 4? I can lose one of them without any trouble at all, which also makes operations easier because now I can think about migrating systems over one at a time. So lots of advantages to doing scale out like that. A version of this is clustering. I'll mention clustering because I need it on the next slide. Clustering is where you have a number of independent computers acting like a single system. There's also a scientific meaning of cluster, but I won't go into that. This is the more commercial meaning of cluster. They have shared storage accessible to all the nodes in the cluster. The outside world sees them as a single system. They've got a single IP address. They provide, through that single IP address, a single set of services to the outside world, and they know how to do failover to other members of the cluster. So there's a heartbeat in this picture between server A and server B. There's a heartbeat signal. They're keeping track of whether each other are alive. And if A goes down, B says, oh, A's dead. I better take over from A. And it will do whatever it needs to do to route the traffic through to itself and grab the storage used by B and take over that as well. So they will grab each other's resources in case of failover. And then internally there'll be some type of load balancing and load sharing between all the members of the cluster. So good, highly resilient, but stateful because all this state is shared between the members. So now, scaling state stores, if I can use clusters, can't do bigger box. Even if I could, it probably wouldn't help anyway because I've probably got locks and I/O limits and things there anyway. So replication's a possible thing. I could have lots of copies of my database server. I could replicate them, and then all my shared storage is replicated at each box. The apps can access the most local state store to them. And every time something is changed, I've got to replicate those changes. So that's a bit tricky, a lot of overhead to do that. But there's techniques, there's log shipping. I can use the transaction log to ship updates across the system. So mechanisms for that. Or I could partition. I say, here's my state store. I want to double its capacity. Customers between A and M, I put to there. Customers between there and there, I put to there. All the customers for the New South Wales stores go to here. Victoria go to here. But either New South Wales or Victoria could take over from each other if necessary. And there's preferably, if the partitioning is transparent, that's a good idea. And if you look at SQL Server and probably Oracle, there's a thing called partitioned views there, where you've taken the tables, you've broken them into individual tables across different databases, but then you've created a view over the top of that, which makes it look like a single table. So as the application program, you say, find something, select something, and underneath it, the database is working out which machine should get that request, but transparently to you. Or some combination of the above. And that's everything put together. So here's our user community. We've got a UI layer, which is a web server farm, some type of load balancing, requests are coming in and being spit out to here. This is just running scripting code. That's my UI layer. It's stateless. Requests can go to any of these. That goes through to a farm of application servers. These are stateless, so a request from one of these can go to any of these, no problem. They're stateless, so they get a request, they pick up the appropriate session state from the database. And over here, we have a partitioned, so we've got two systems, districts 1 to 10, 11 to 20, and each of those is clustered. There's shared storage and a two-way cluster between each of those. So if we take a gun and shoot that machine that's running there, that's okay. That won't pick up the workload. So that cluster will fail over nicely, and these are all disposable as well. So by combining partitioning and clustering and scale out of stateless servers, we've got a robust and scalable system. And we must be pretty close